Of all the great flyers the world has ever known, it may come as a surprise that one of the best aviators in the animal kingdom doesn't even possess wings. Spiders, instead, use long fans of silk to carry them through the air, often for many hundreds of miles, in a process known as ballooning. They have long been known to have flown the nest in such a way. Charles Darwin himself marvelled at hundreds of tiny spiders landing on the Beagle while out at sea, and later recorded how they took off from the ship with great speeds even on a calm, windless day. During this time, there were two theories for how ballooning worked. The first theory, and the most obvious explanation, was that long strands of silk emitted by the spider catch the wind and the associated drag forces pull the spider aloft. But spiders will only balloon on days where the wind is a gentle breeze, which raises the questions of how there'd be enough force to pull the silk from the spider's spinnerets, and how could heavier spiders even become airborne at all. The second theory was that atmospheric electricity could also provide the force needed to get the spider aloft. Similar to how your hair lifts to stand on end when you rub a balloon on your jumper, spider silk could be lifted into the air by natural electrostatic forces in the atmosphere. These electric fields are present at all times all around the world, but are most noticeable during thunderstorms when they are at their strongest. Surprisingly, until now, the electrostatic theory of spider ballooning had never been tested. In our lab at the University of Bristol, we isolated spiders from any airflow or atmospheric electricity and generated our own controlled electric field at levels found in nature. In response, the spiders began to change their behaviour to perform tiptoeing, where they straighten their legs, raise their abdomen and release silk. This behaviour is only ever seen when a spider wants to balloon. Furthermore, once the spider was aloft, its altitude could be controlled by turning the electric field on and off. This demonstrates that spiders can balloon using electrostatic forces alone, but in all likelihood, they would use a combination of both wind and electricity to balloon in their natural environments. So how do the spiders detect these electric fields? In this experiment, it was also observed that the minute sensory hairs on the spider's exoskeleton were similarly moved by the electric field. We can then infer that spiders can feel the charge in the air using the same sensory hairs they would use to detect a breeze. The results of this study show us that electrostatic forces could be an integral part of spider ballooning. And by fully understanding the mechanisms behind it, we can better describe population dynamics, dispersal, and ecological resilience, all of which are important for global ecology.